Hey everyone, welcome to another duality repair video. This is Nick. Tonight I'm going to be repairing a benchtop power supply. So believe it or not, I don't have a benchtop power supply. Every electronic technician should. So I bought this off eBay for parts, and assuming I can fix it, I'm going to keep this one. So it's obviously not in the best cosmetic condition. There's a few dings on the cover, some tape adhesive residue there, but all that should be able to come off, so it should look pretty clean. If I can get it repaired, I'll clean it up. So let's just jump straight into the symptoms. So I'll power it up. Obviously I have my multimeter hooked up, and I started off with the voltage and current set points all the way counterclockwise, so they should be at 0. And so we have our voltage output here, and you can see my meter here. It's reading, it's tracking very well. And then of course 0 milliamps. So let's see what happens when I turn up the voltage here. And I should have mentioned the specs. 0 to 60 volts DC at 0.5 amps. That's range 1. Range 2 is 0 to 120 volts at 0.25 amps. So not a high-powered device, but certainly a really nice voltage range. So again, you can see the voltage tracking with my meter here. Let's start cranking it up a little bit. So I am on range 1, the 0.5 amp range, which is 0 to 60 volts. So a full turn of this pot, this is a 10-turn pot, so a full, the full cycle of this should bring me up to 60 volts DC. And so let's watch. Again, tracking well. We're at 0.9 volts, we're at 1 volt and 1 volt. That's looking good. You can't tell how much I'm turning it, but I am turning it a lot. I bet I'm very near the range already. And I should be at much higher of a voltage. So this is going to be, there it is. So I'm at the very end. And actually I turned it on and tested it earlier, and it was getting to 8 volts. So this is just crazy. So obviously it's not able to reach the set point voltage at all. And the other thing that this thing has is, so it's got constant voltage mode, which is just, whatever your voltage is set to, it's going to keep that voltage maintained regardless of the load, assuming it doesn't go past your 0.5 or 0.25 amp rating. And then it's also got a constant current mode, which is set by this button here, so you should just be able to hold it in and adjust the current knob for your desired maximum current. And so if you were to adjust this to, say, 100 milliamps, the voltage would it would put out whatever your supply is, whatever your set point is, unless it hits that 200 milliamp mark. At that point, it would do whatever it has to do to keep the current at 200 milliamps or less. So if it has to drop the voltage, it'll drop the voltage. And so I should just be able to hold this button and turn it, and it should go all the way up to 500 milliamps as a constant current set point, and it's hardly doing anything. You can see it move just barely. So none of this is working at all. This is actually behaving worse than it did earlier. So something might be getting worse. I'm going to power this off now that we've seen the symptoms. Let's open it up. I do have the schematic, but let's open it up and take a look at the internals. I have no idea what we're going to find in there. Here's the supply with the cover off, and it does pass the smell test, but it does not pass the visual test. So I look for any signs of heat damage, anything like that. I didn't find anything like that. I didn't find any bulging capacitors, but what I did find was this one, and you can't pick it up too well on the camera, but this one right here has definitely leaked out of the bottom. So you can maybe pick up this residue if you look on this chip. See if I can clean some of it off. A little bit. So you can see I'm scraping it off. There's a bunch of residue all around this area, and it's emanating from this capacitor, the base of this capacitor, and I can see tons of really dark looking sticky liquid, and that's going to be a blown capacitor more than likely. So let's take a look at the schematic. I guess we can look around supply really quick. So obviously we have the main transformer coming in, huge. It's only 30 watts, 30 watt power supply, so it's a pretty big transformer for that. We have a transistor here and here. Those are going to be our drive transistors, and obviously just a couple of capacitors here. This one's going to be our main filter capacitor from the supply to ground. So you got that main board on the bottom with all your power capabilities, and then you have the front panel board here. That's got all your controls on it. You can see it's got a few chips on there for control there. And really, there's not that much to it. So take a look at the schematic here. So this is, the silk screen tells me this is capacitor C7. So let's take a look at where that's at. So first of all, the schematic in general, we'll start off here on the left. Power coming in, AC power coming in to the main transformer here. And it's got 3 legs, 3 outputs. So we have one supply up here at the top, one in the middle, and one on the bottom. We'll start at the top. One at the top is the, as it's labeled, the display power supply. So it comes in through a fuse, has its own bridge rectifier, has its own regulator, and then it spits out 5 volts. And so that's what's going to be going to the display. So we're going to have, among other things, some communication or some other signals. We're going to have 5 volts from this board to the display. Second part of the transformer's output here is this section, and as you can see, it's labeled reference and bias supply. And so same thing as up here, we come in through a fuse, and actually 2 fuses, and we have a bridge rectifier again, and so we're going to come in through this upper portion, through this regulator here, and we're going to generate 12 volts as well as 5 volts. So this regulator is actually going to generate the 12 volts, and this zener right here is going to regulate or create the 5 volts. So these are going to be reference signals that we'll see later on down in the circuit. And then down here on the bottom leg, we have another regulator, which is going to output our negative 12 volts. And then you have your bottom portion of the circuit, which again has its own fuse. No, doesn't have a fuse. But this is our current selection switch, so either 0.5 or 0.25 right here. And again, it's got its own bridge rectifier. And we come in, here's that C2, that's this big capacitor right there, C2. That's the one right across the output of the bridge rectifier. And so this is going to be our actual power output, our power supply right here. And so it's got this part labeled into several sections. We have the series pass transistors right here. Okay, and so this is what's going to be driving the output. And we have our actual driver, which is going to drive the transistors. And over here on the right, we have our voltage error amplifier. So it's going to have our voltage control, which is just our voltage control knob on the front. And this is going to feed an input to this op-amp. And the op-amp is going to pull in, it's going to sample the output and compare it to what our voltage control knob says it should be and output accordingly. And so that's going to come out here through the bottom to this driver transistor Q2, which is going to drive the series pass transistors. And so you'll see here, down here in the bottom in the voltage error amplifier, we have plus 5 volts. That's reference voltage from up here. So very, very important. This is very necessary. We have plus 12 and minus 12, which is from the reference down here. So plus 12 and minus 12 in the driver circuit. And then we've got these other circuits as well, as other portions of the circuit. So we have a current error amplifier, which is just like the voltage error amplifier. But when set in current, constant current mode, this is going to be in effect. And this, so this is going to sample the current at your output. And if it exceeds the constant current rating, whatever you set it to, this is actually going to cause the driver to reduce the output voltage. And then we have a few other tiny circuits here, parts of the circuit. The meter input circuit, so this is what's measuring the current and the voltage. And then we have our CV, or constant voltage, CC, constant current indicator circuit. So this is literally just going to tell us if we're in constant current or constant voltage mode. And so these are just getting feedback from the circuit telling you, and they'll display, they'll illuminate an LED when certain conditions are met. So now let's take a look at, again, this was C7, the one that's leaking. Where is C7? Well, I found it. It's up here in the reference supply. And so C7 is right here, and you can see it's filtering this this output to this regulator right here, which is feeding our 12 volts and our 5 volts. So extremely important. Now, where does the 5 volts used? Again, it's used down in this voltage error amplifier circuit. If this 5 volts is all messed up, if it's unfiltered, we're going to get really goofy signals coming into the op amp, and it's not going to know how to drive based on this reference signal. So this makes sense for why we're getting very strange output voltage. It's also, again, part of the positive 12 circuit. And what else uses that? Constant current. The current error amplifier circuit uses plus 12, and so does the driver. And so if both of these voltages have some issues with them, these circuits are not going to behave normally. So it all kind of makes sense. I took a quick look around. I didn't see anything else wrong with the board. Obviously, these are the same capacitors here. This is C13. Let's take a look at where C13 is. C13 is just below C7. So here's C7, here's C13. C13 is going to help excuse me, is going to help filter out the negative 12 supply. So they're not quite the same. This is 330 at 35 volts, and this is 470 at 50 volts. So they're different ratings, but they basically have the same importance. So this one didn't appear to leak, but if I have a spare, I'm going to replace that as well. But first things first, I'm going to take this out, clean the board up, replace this, and see if that helps. I'd say that thing's toasted. That's nasty. So let's go ahead and get that replaced. So this is a 330 microfarads at 35 volts. It is a Nichicon, so it's a good brand. And 105C. I think I have a direct replacement. One extra from an amplifier that I was recapping a while ago. And 330 at 35 at 105C. I do. The package size is definitely different. It's narrower and longer. So the new one's on top there. Much smaller radius. But shouldn't be a problem. There's plenty of, there's no restrictions on height here because the highest thing in here is the tallest thing in here is that main filter cap and the transformer. This is nowhere near that, so this is going to be good. This will help. So I'm not sure how I didn't notice this before, but and maybe you did. You can see the copper right here. The copper trace is exposed. You can see where the capacitor leaked, and it leaked out over this trace, and it just started eating the trace, the cover of the trace here. So the trace it looks to be intact, but it's no longer coated. So that's interesting. I'm definitely going to examine the that path and make sure it does have continuity. I'm not aware of any process to cover that up again. So I may just have to live with an exposed trace like that. It's unfortunate. Definitely going to want to make sure I clean all of that up, because any remaining electrolyte there will eat up any other trace around it. I can see it leaked over here. This is just the mount for the heatsink for this. It's one of the rectifiers here. So it's kind of starting to eat that away too. So I'm going to clean up as best I can. I may even have to remove it just to clean it up really well. But yeah, that's bad. That just ate right, ate straight through to the trace there. So interesting. Okay, we'll keep moving here, keep cleaning. Alright, I cleaned the board up, installed the new capacitor, and I powered it up, so let's see what happens here. Nope, no change. So that's probably half its range right there. It should be at 30 volts by now. Let's change the range. It doesn't do anything. It should just double it. See if we get anything on the current set. Nope, that didn't change either. So we have another issue. That's okay. That capacitor is obviously bad. Let's look at it one more time. Look at all that. Nasty. So what's next? Let's take a look at the schematic again. And I saw some test points on there, so we'll check voltages, check the reference supply voltages, some other test point voltages, and just keep moving forward. We'll figure it out. Okay, first place I'm going to check is between test point 1 and test point 5. So that's the positive 12 and positive 5 volts of the reference supply. Since those are the two voltages that are directly in line with this capacitor that was leaking, I'm going to start with those, and supplying the reference voltage is extremely critical, especially for the voltage area amplification circuit. So let's check that out. I have the jumper here from test point 1, which is positive 12, so I'm going to go to test point 5, which is positive 5, so we should have a 7 volt signal here. Test point 5 is right here, and nothing. That's no good. So again, both of those are driven by that same regulator. The 12 volts is driven directly by the regulator, and the 5 volts by the Zener. But so that's not getting voltage. So maybe there's something wrong with this. This is the regulator here. I'm going to go back. This has the fuses right here, F2 and F3, or excuse me, F1 and F2. Let's check those out. Power this unit off here. Let's jump between the fuses. F2 and F3 are, and I'll zoom in, so you don't need to see the meter for continuity checks. You can see F2 and F3 there. Certainly expect that they'll be okay. Well, you know what? That's all that leaking capacitor right there. Who knows what happened? Let's take a look. Okay, F2 is open, and F1 is open. Sorry, you can't see that. So I checked these two fuses here. They're both open. And let's make sure my meter's working correctly and I'm not going crazy here. Let's check F3. F3 is the fuse for the display power supply, which we know is working because the display displays. So that's right here. Yeah, so that's fine. So these two fuses are blown. I found some pico fuses in a spare board that I had laying around. They were 2 amps, so I'm a little worried about that. But, it's not terrible. I'll turn it on, and if I smell anything, hear anything funny, I'll turn it off right away. So let's give it a shot, though. It's plugged in. Let's power it on. Interesting. So we're in constant current. Oh wow. Okay. So this is different. We never had this before. We're in constant current mode. I believe because our current knob is all the way at the bottom. So let's see if we can. It's not going to let us adjust the voltage. Let's see if we can adjust the constant current set point. Yes, we can. The only thing I don't like that's definitely off. The scaling is off. So you see we start at 242 milliamps. That's all the way counterclockwise. And we hit 500, and I can go well beyond that. 726 to 236. So it's about 500. So something's a little off there. Maybe it's just the pot needs to be adjusted a little bit. I don't know. That's definitely different. But let's tweak this up to 400 just so we can see if we can get an output. Okay, so it at least is reading 0 milliamps output. Let's see if we get a voltage. Much better. I barely turned that, and I'm getting an output voltage here of 2 volts, 3 volts. Still not registering anything on the current output, which is good. It's not tripping anything. No shorts. And I maybe turned it 1 or 2 full revolutions, and we're at 20 volts. That's good. Probably a good time to plug in the meter and see if it's accurate. So let's do that. I'm going to power it off just while I do that. And since it's been on, I haven't smelled anything, so that's good. Things seem to be behaving better anyway, minus the constant current set point is obviously off. Let's hook these up to the meter. See if what the supply is reading is accurate, or at least as accurate as my meter is, which, you know, isn't the best, but it does the trick. Let's put the meter in there. So I'll start in the 20 volt range, and I'll turn it all the way down again. It's powered on. Okay. Set it to 5 volts. 5.04 volts on my meter. That's good. Let's go to 15. .04. Good. And let's go up to 50. See if we can get up that high. Still not reading much on the current. 0.1 to 2 milliamps, not a big deal. Okay, 50 on the dot. Okay, that's great. Let's see if it'll go to its full range at the 0.5 amp set point of 60 volts. It gets there, and I'm reading 59.99. Let's see if it goes past it. It does. So that's just going to be your different current set point. So we should be able to get up to 120, ideally. We're cutting out there. Maybe I have to be in the other range. Let me go back down to 60 and change the range. Okay. We're at 60, 70, 80, 90, 100, 10, 15. Okay, goes a little bit beyond 120. What does that actually get to? So all the way all the way clockwise gets to 136 volts, and how accurate is that? Fantastic. 136.5 on my meter, 136.9. Yeah. They're within 100 millivolts really of each other. It's fantastic. That is good. So we've definitely resolved one issue. The capacitor caused the fuses to blow. We replaced the fuses, and now everything's working. We have our reference voltage. We have to. They may not be perfect. We haven't checked that yet, but they're definitely working. The output is accurate and is able to output the full range, 0 to 120 volts. We don't have any shorts because we're not drawing any current at any voltage output, which is good. There's at least still one issue remaining, and that's this constant current. Again, I'm all the way counterclockwise, and I'm starting at 242 milliamps. And fully clockwise, I'm at 732 milliamps. Curious what happens if I change the range. Let's change the range. So at the 0.25 amp range, our constant current set point goes from 245 to 490. And again, at this range, the 0 to 60 volt half amp range. We're at 245 to 737. So that's interesting. Something still potentially wrong in the current error amplifier circuit. So what, well, let's take a closer look at this circuit here. So here's where you're setting constant current, right? And it's going to be reading based off these this resistor divider here, and then your other point comes in here. This is where you're getting your current reference. So we'll take a look at this constant current set circuit as well as the meter input circuit next. I may have found the issue of why the constant current set point is reading abnormally, specifically reading above 0 when it should be 0. So if we take a look at the schematic, over here on the right, we'll see our constant current set point. When I depress the switch, it's in this upper position, and it's measuring between this pin and positive S. That's what it's measuring for that constant current. So let's follow it over here, and we're reading right off of the center tap of the potentiometer R20. So when I was adjusting R20, that's how I was able to get a 0 point reading here, which is good, but it did adjust my range. So my range, it no longer went from 0 to 500. It went from, when I was able to get it to read 0, it was like 0 to 100 or 200 maybe millivolt range. So that doesn't work. So if we look at this specific part of the circuit here, there's only a few things really that could cause this. And so again, it's reading between positive S and the center tap of this potentiometer, which is right here really. So really it's dependent upon the voltage drop across this right here. And so what could affect that? Well, the potentiometer itself, or theoretically R40. If this is, defective in some way, that would definitely cause a difference in the voltage drop there. So let's take a look at R40. And it's way up here on the board. And you probably can't see the bands, but it is red, blue, violet, orange, which is 267K. And if you see there, I'm in the 200K range and I'm at 42K. So that is not reading correctly. Let's go to the 200K range. Yeah, 44K. Not even close. So what is that, maybe 20%? So if we go back to the schematic, we go from a potential, the resistance across this, TP6 or test point 6 to test point 7 of a little bit over 300K. So what is that, 317K. Now with this at 44K, we're now, the maximum drop is only 94K. And so the ratio between this resistance and this resistance is almost equal now, where before this would accommodate most of the voltage drop. This is now accommodating most, or at least half of the voltage drop, and that's not what we want. So I already looked through my bin. I don't have a 267K resistor. I don't have anything close to that. I couldn't find a pair of resistors that would get close to 267K. So really I'm just going to have to order one and install it, and we'll see. I looked at some other components in this part of the circuit, and everything seems to be fine. These potentiometers seem to be working fine. R33 is exactly what it should be. And same as R28, those are both what they should be. The other thing to note, if you look on the board here, so here is the capacitor that I replaced that leaked. Here you can see how the bare copper trace there where it ate away. And then here's our R20, and here's R40. And some of that electrolyte, although you can't really tell it, there was a very thin layer of film kind of all around this area. including over R20, or R40, excuse me. So potentially could have got damaged due to that. Just to be sure, I'm going to remove it, make sure it's reading 44K outside of the circuit as well. Highly confident it will. And if so, definitely going to order that and replace it. So let's remove that quick. I removed the resistor and measured it and determined that that is not the fault. It is reading as advertised at about 267K ohms. And so I reinstalled it. I looked at the schematic and I realized what I was measuring. Although I was measuring across R40, I was actually measuring around the circuit here through all these resistors back to the other side, simply because it's the path of least resistance. So if you add all these resistances up, it's much less than 267K, which is why that's what it was measuring. It's in the 40 to 50K ohm range, and I can prove that by measuring across R40 and adjusting the current control knob here, and you'll see the resistance change. So let's go across R40, if we can get there. There we go, about 44K. And I'll adjust the current control knob. You'll see it go up to 48, almost 49K, and go back down, and back to 44K. So that's what I was measuring there. That resistor is just fine. What I did notice, let me power it back up. Let's look again at the current symptom. No pun intended. Power it up. So with CC set to pressed, my milliamp reading is way off, but more concerning is the fluctuation. It's not just a fluctuation, it's a constant decrease. And it starts to slow down, but originally I thought it might be a capacitor simply discharging, and obviously it shouldn't be happening, but it's kind of what I thought. But I think I know what's going on. So if we go back to the schematic again, where I'm getting voltage is right here. In between R40 and R20, I'm reading voltage because, again, if we look over here, our constant current set is reading between positive S and the center tap of R20. So that's just really test point 6 to the center tap of R20, which means there has to be a voltage at the base down here of R20. So when I measure voltage here, I get a voltage. When I measure voltage on the other side of R40, I get no voltage. How is that possible? Our 5-volt rail is up here. We're coming down through all these resistors, and we should be dropping all the way down to the positive S at test point 6. But yet I'm getting a voltage injection in between R40 and R20. Didn't really seem possible. So then what I did, so I'll put my positive lead on the 12-volt rail, and you can see that when I go to test point 6. Sorry, my hand's kind of in the way there. Alright, I have my positive lead hooked up to test point 6 here, and then I'm going to probe around here. So let's look at R40, and there's our voltage. Around 300 volts. Millivolts, excuse me, millivolts. Okay, and the other side of R40, nothing. So somehow I have voltage coming in here and then dropping here. Doesn't make sense. It's actually dropping across R20 to plus S. So how is that voltage getting here? There's no place for it to be injected here. So with my probe on test point 6, I can probe around the board, and that's just crazy. You probably can't tell. Let me zoom in. So look, keep the voltage in mind. Look what I'm probing. That's just the surface of the board. That's not a contact. That's not solder. That's nothing. So there's a voltage between test point 6 and the, look at that one. Started off at 12. Again, I'm just touching the board. So what's happening here? Well, the cap that burst right here the electrolyte, it didn't just kind of eat away above this trace here. There's some residue all around this area of the board, and I wasn't able to clean it effectively, having all these components mounted. So it's forming a conductive path between especially between this exposed 12-volt rail and anything that's conductive. And so what's happening is the 12-volt rail is being bridged partially across the board via the electrolyte to this potentiometer. This is R20, and probably other components. And so again, if I probe, this is to the board. This is test point 6 to the board surface. As I go further out, you'll see I'm still touching the board, but I'm at 0 volts simply because I'm outside of the spill zone of the electrolyte. You can see it's dropping. If I go further out, dropping, go way out, almost have no electrolyte there, and now if I go way over here, I should have nothing. Yeah, there's no electrolyte over there. So what I'll need to do is remove all the components in this area and really clean the surface of this board here to remove all of that electrolytic deposit. That's the film that's just sitting on the board here. Again, I did the best I could. I cleaned off this area pretty good, but I'm going to have to clean all this up really well. And I think that's going to resolve this issue. And after that, we're going to be good to go. And this power supply is going to be ready to be put into service here on my bench. So I'll be back after probably after I clean these, or after I remove all of these, and I'll clean it up, and we'll test it once I get back. I pulled most of the components in this general area where that capacitor had leaked, including C13 over here, which, as you can see, also was leaking. And you can probably see a little bit of corrosion here, starting to eat away at the cover of the trace there as well. So I'm going to replace this while I'm at it. I cleaned the rest of the board up. It looks much better, including, so you can see here, if I zoom in, that's about as close as it gets. This is the center tap for the R20 potentiometer, and here's the 12-volt rail. You can see how close they are. All it takes is a little bit of electrolytic fluid, and really it's this exposed trace to there, so you got about, I don't know, 4 millimeters, just a few millimeters of space there, where if it's coated in that electrolytic film, it's going to be conductive, at least somewhat. So that's, I believe that's what was causing the voltage leakage across there. So I feel pretty good about removing those, cleaning it up. I think this is going to work. I'm going to go ahead and put everything back together and we'll power it up. Alright, the board's been cleaned. I reinstalled all the components, including a new capacitor there for the other one that was leaking. So, moment of truth, let's turn it on. Ooh, it's a good start. So I'm holding in the CC set, and I have 0 displayed there. Let's see if I can get a current reading. I can. Great. Goes up to 520 and back down to 0. And let's go to the other range, the 0.25 amp range. Still reading 0. And 266, just above a quarter amp. Looks great. Alright, so that's working well. Let's make sure the voltage output is still working. I'm on the 60 volt range. It's pretty good. 62.5. How high does it actually go? It's pretty high. Let's go to the other range. 0 to 120 volts. $128. Great. Alright, so it looks good. Last thing to do is to hook up a load to it, make sure it can take that, and then this thing is fixed. I am going to do some cosmetic repairs. So these, this one's actually busted. You can see it's kind of bent in pretty good. I don't know what happened there. It got smashed. It almost looks like it got melted on the tip there. This one looks pretty worn as well. This one's in good shape, but I'm going to replace all three of these at the same time. I'll clean up the, really clean up this front faceplate with some alcohol as well as this tape residue on top. And the bottom's missing feet, so I'll add those. Otherwise it's in really good shape. So let me hook up a load and we'll test that. Alright, before I hook this up to load and test the output, I thought I'd calibrate the voltage output first. So service manual has you connect the DVM and the multimeter across the output. Adjust the voltage in low current mode until your multimeter reads 120, and then adjust R10 on the back of this front panel until your front display also reads 120. So we'll do that now. Found R10, and let's adjust. I was messing with some of these pots earlier when I was looking at the constant current setting. I believe I adjusted this one as well, so that's probably why it's so far off. Alright, 120, 120. So let's just go to, say, 90, see where we're at there. 90 and 90.1 on my meter, very good. And let's go to higher current range, see where we're at say 60. 60 here and 60.1 on my meter, very good. Let's go to 30. And 30, excellent. 15. 15.0 and 15.0. Let's go down to 5 volts. See how accurate we are down there. 5.0, 5.0, and let's go to 2 volts. How about 3.2? That's a pretty common voltage. 3.2, 3.2. Alright, I'd say the voltage output is calibrated very nicely. There is a calibration procedure to adjust or calibrate the current reading as well. That requires a 0.1 ohm at 1% power resistor, and I don't have one of those in the moment, so I'm going to leave that for now. So I'll just skip to hooking up a load, and we'll see where we're at there. Alright, the only load I really have for testing at this time are 4 8 ohm 50 watt power resistors for testing audio amplifiers. So I'll use those in series to make up a 32 ohm power resistor. And so I'm not going to be able to test the full voltage range, but I should be able to test good enough for this purpose. So let's start off, let's go to 5 volts. That's handling just fine, 154 milliamps. Let's go to 7.5 volts. Still okay, 227 milliamps. 10 volts, 300 milliamps. And let's make sure that at about 500, well, let's see. At 528 milliamps, we should cross over from constant voltage mode to constant current mode, and that'll drop my voltage or keep my voltage constant at that current. So let's see. Again, 528, we should cross over to constant current, and my voltage will no longer increase. Almost there, we're at 17. Okay, so we're there. So it happens at 520. Yeah, and I can turn it all I want. Voltage will not increase past 17.2. Okay, so that's working. Let's check the low current range. And really this should behave the same. Actually it'll behave a little bit differently because the low current range, my current limit is 270. So now I'm going to drop out even earlier. So let's make sure we drop out around 270. We cross over to constant current. That's going to be less than 10 volts. And there we go. At 260 we cross over, and that's about 8.7 volts. So it is working beautifully, and this repair is done. To summarize or recap, no pun intended, I did have to recap two of these. Two on the power rails. Let's see here. Look at the schematic. C7 and C13, both of these. So these, the C7 is feeding the plus 12, plus 5 in the reference and bias supply, and C13 is feeding the minus 12. Not feeding, but filtering. So both of those leaked. C7 was by far the worst. C13 was starting to leak as well, so definitely needed to be replaced. And then as well as the leaking here caused havoc around the close proximity of that circuit as well. It wasn't just the capacitor itself; it was the conductive electrolyte that leaked out, crossing over traces, especially the exposed trace, and onto the potentiometer here, R20, causing the constant current readback issue. So this one's fixed, all done. Stick around for the next video. I have several more coming up. I'll have part 2 of the Tektronix 2213A repair coming up very soon, waiting on that board. And then I'm very excited, I have another Tektronix TDS 420 coming in that I'll be looking to repair, as well as a lot of 6 I believe Agilent digital multimeters, benchtop multimeters. So that one will be interesting. So stick around for those. Give me a thumbs up if you liked it. Questions, comments in the comments, and subscribe if you haven't subscribed. Thanks for watching. We'll see you in the next one.